In previous sections, we found the derivatives of exponential functions, which are inverses of logarithmic functions, and of inverse trig functions. Now what we want to do is we want to find the derivatives of more general inverse functions. And so let's take a look, first of all, at the definition of an inverse, just to remind us of that. That we would say that if g evaluated at f of x is equal to x, and this symbol just means for all x in the, you can think of this as in the or as an element of the domain of f, and f evaluated at g of x is equal to x for all x in the domain of g, then f and g are inverses. Okay. And we write that g is equal to f inverse of x, or we could have said f is equal to g inverse. And so that's the definition. By the way, think of what happens here. All right, f is doing something to x. It's applying some operation on x and getting a result, and that result is f of x. Then if you apply the operation g to that result, you get back to x. So f and g undo each other, and this says the same thing in the other direction. If g does something to x and f undoes it, it's sort of like addition and subtraction. If you add 5, you can undo it by subtracting 5. That's how inverses work. All right, but there's another characterization of inverses. All right, and that's this. Let's suppose that y is equal to f of x. All right, now think about any ordered pair xy that satisfies this relation will also satisfy this one if I apply f inverse to each side. But remember, inverses undo one another, so the right side is just x. So we'd have f inverse of y is equal to x. These equations are equivalent. If an ordered pair xy satisfies this first one, that ordered pair will satisfy this last one. All right, and if an ordered pair satisfies this last one, it will satisfy this first one. But now compare with y equals f inverse of x. All right, these relationships are not the same. Notice the x and y have been switched. All right, again, we can look at it clearly here. Instead of f inverse of y here, we have f inverse of x, and instead of f inverse being equal to x, it's equal to y up here. So the roles of x and y have been switched. And that's another characterization of inverse functions. We switch the x and y. Now, here's a question. All right, when does a function have an inverse? In other words, when is a function invertible, we'd say? Well, if we look at this, all right, let's take a look at this function. This line here will be here in all of the examples. This is the line y equals x, and this is just a linear function. If I would invert this, if I interchange x and y, when you interchange x and y, it just reflects this graph across y equals x. And so if I interchange x and y, it looks something like this. All right, notice this line is a function, the inverse relationship. After switching x and y, here's the original, the red is the original, now the blue one is the inverse relationship, and this is a function because it passes a vertical line test. Any vertical line will hit it in at most one place. Well, now if we think about this and switch it back, in order for the inverse relationship to pass a vertical line test, the original relationship has to pass a horizontal line test. So for a function to have an inverse, which is also a function, all right, it has to pass a horizontal line test. Let's take a look at a couple other examples. All right, here's the example, x squared. Obviously, x squared does not pass the horizontal line test. If I interchange the x's and y, I don't get a functional relationship because the relationship doesn't pass the vertical line test. I get a relationship, but it's not a function. But now what do we do? Sometimes we can fix things up so that we have a function. One way of doing that is we can fix it up by limiting the values of x that we'll consider to be allowable. All right, and if I limit those to the values of x greater than or equal to 0, if I limit them, now this does pass a horizontal line test. So the inverse interchanging x and y in this restricted relationship, right? It gives me a functional relationship that passes a vertical line test. All right, the same sort of, well, let's see, if I look at the exponential function, I better take off my restriction here. If I look at an exponential function always passes the horizontal line test, so its inverse, which is a logarithmic function, will pass the vertical line test. It's a function. So exponential functions are invertible without any restrictions. Now, if I look at sine does not pass the horizontal line test. Notice the horizontal line hits it in two places. So if I would just invert this relationship, I'd get something that's not a function. It wouldn't pass the vertical line test. But I can restrict sine, all right, in such a way, if I restrict it in here till I get to this bottom point, which is at x is equal to negative pi over 2, and this restricted here till I get to this top point, which is at x is equal to pi over 2. Now it does pass the horizontal line test. So if I invert this restricted relationship, if I invert this, then I still get a function. This is what your calculator calls sine inverse. It's the inverse, the interchanging of x and y in that restricted relationship, sine of x from negative pi over 2 to pi over 2. All right, let's put things back. The same sort of thing happens, all right, here if we look at cosine. Cosine does not pass the horizontal line test, so its inverse, interchanging x and y, its inverse will not pass a vertical line test. Its inverse will not pass a vertical line test. And we can see that the vertical line hits it more than one place. All right, but we do the same thing. We restrict it, and here's how we restrict it. We bring it in basically to this high point here, and we start with x at 0. And we start with x at 0, and if we restrict cosine to be just the part where x is between 0 and pi, then we do have something that passes a horizontal line test, and it is invertible. So its inverse will be a function. That's what we mean really by invertible. It has an inverse, and its inverse is a function. So here's the question: when does the function have an inverse? All right, and the answer is when it passes the horizontal line test. Okay, when it passes the horizontal line test, it's invertible. Another way of saying this is passing the horizontal line test is equivalent to what mathematicians would say being 1 to 1. So maybe a quicker way of saying passing the horizontal line test is saying that a function is 1 to 1. If it's 1 to 1, it passes the horizontal line test. If it passes the horizontal line test, it's 1 to 1. Okay, let's take a look at this function. Now here's a question. We're eventually going to want to find the derivative of the inverse of this function. F of x is 3x cubed plus 6x minus 2. All right, and we want to find it at x is equal to 7. Now, a preliminary question might be, does this function have an inverse? Before we go to the bother of trying to find the derivative of the inverse, we might want to know if it has an inverse. Now, we can answer this question by taking the derivative of f. If I take the derivative of f, I'll get 9x squared plus 6. And if I look at that derivative, notice it's a square times 9. Square is never going to be negative. 0 at the smallest. It's 0 or positive. Times 9 is 0 or positive. And if I add 6, this result is always positive. It's always greater than 0. So the slopes of the tangent line are always greater than 0. That means if you think about it, then we'll take a look at this relationship. Here it is. If the slopes of the tangent line are always greater than 0, always positive, it has to pass the horizontal line test. It has to be 1 to 1 because the thing is that it can't double back and go back down so that we'd have a place where it would violate the horizontal line test. So if the derivative of a function is always positive, it passes the horizontal line test. If the derivative of a function is always negative, it passes the horizontal line test. In other words, if the derivative is always positive, it's invertible. If the derivative is always negative, it's invertible. Okay, we'll continue this in the video is getting a little long here, so I'll stop at this point and we'll continue this. We'll find the derivative of that function in the next video.